Okay, so we're talking about hypothesis testing, and there are really two approaches to this. One is called a critical value approach, and the other is called a p-value approach. First, let's talk about the critical value approach to hypothesis testing. What does it mean? Well, our criteria for deciding whether or not to reject the null hypothesis in this kind of test is based on a z-value. That is, it's based on a value under our normal curve. And we're going to use that to test whether or not we are in a region where either we reject the null hypothesis, and the probability of that, that the mean is within that region is very low, or not reject the null hypothesis. Right? So the separating quantity for us is this number right here for that critical value, right? It's a z-value. We're looking for z-values and comparing them in the critical value test. This is sort of the traditional method. And what we say is that we will reject the null hypothesis if we find a z-value from our test statistic that is lower than that number. And we're not going to reject it if it falls higher. So we're looking specifically at the z-scores along the bottom axis of this normal distribution. We say the rejection region is the set of values of the test statistic that leads to a rejection, a non-rejection region being the set of values that leads to non-rejection, and of course the critical value is the value of the test statistic that separates the rejection and non-rejection regions. Now, in fact, this number right here, we might also be talking about a t distribution as well, and it works the same way. But what's going to change there is the shape and type of number that we get is going to be based on the number of degrees of freedom, that is, on the sample size itself. Graphically, the way we're going to deal with it is either using a two-tailed or left or right-tailed, one-tailed test. In a two-tailed test, this first one right here, our rejection region is based on either being high or low. That could happen, right? We say that we could have a mean that's too high or too low. It's kind of like setting up our confidence interval and looking to see whether or not the mean that we get from our test statistic is actually either too high or too low as compared to the critical values that we find along the base of our normal curve. If it's a one-tailed test, like a left-tailed test, we're testing specifically to see whether or not the mean is less than what we say it is. So in this situation, we're looking to figure out whether the alternate hypothesis is one where the population mean is less than a given value. Right? And consequently, if we're in a right-tailed test, our alternate hypothesis looks like this one where the mean is greater than some given mean here from our test statistic. Okay. So to obtain those critical values, what do? The hypothesis test to be performed is the significance level alpha. That critical value must be chosen so that if the null hypothesis is true, the probability of alpha of the test statistic will fall in the rejection region. Okay. So what we're looking for are one of two possibilities whenever we're dealing with our critical value z-test. It goes like this. We say that in this case we're going to reject the null hypothesis, and if our null hypothesis is that the mean is equal to some given mean value that we're testing for, some claimed value, then our alternate hypothesis in case A is going to look like the mean, well, just simply doesn't equal that mean value. And what's going to happen is that our rejection region, when we get our test statistics will fall either to the left or to the right of z alpha over 2, right? So we're going to depend on z alpha over 2 in the two-tailed test. As far as the one-tailed test, right, in this case, we could be testing something like our mean is claimed to be greater than some given mean. So that's our null hypothesis. And so our alternate hypothesis is going to be that the mean is less than that given mean. right? On the other hand, right, same deal, our null hypothesis in this case is going to be one where the mean is less than some given mean value, and the right tail, our alternate hypothesis, is going to be favored if the mean is greater than that. And then we're looking at that probability, that z alpha value, to demarcate for us where that's going to occur. Now, the other approach is called the p-value approach, and the p-value approach here is based on the probability value. That is the probability that we're going to be less than some number. So in this case, we're not dependent so much on the z-value. We want to find out, well, what is the probability associated with this z-value? The p-value of a hypothesis test is the probability of getting a sample data at least as inconsistent with the null hypothesis, that is too high or too low, as compared as the sample data actually obtained. So we use the letter p to denote the p-value right here. That's the test statistic that we want. If the p-value is less than or equal to the specified significance level, then we reject the null hypothesis. Otherwise, do not reject the null hypothesis. In other words, if p is less than alpha, or alpha is greater than p, reject the null. Otherwise, do not reject. Very often, we've used this little saying in statistics. It goes like this. If the p is low, the null must go. Now, if we say how low, well, p has to be less than alpha for that to be true, right? And that's where we reject H0. Okay. Now, the p-value is an observed significance level. The p-value of the hypothesis test equals the smallest significance level at which the null hypothesis can be rejected. That is the smallest significance level for which the observed sample data is in the rejection region of H0. So, to determine the p-value of a hypothesis test, we assume that the null hypothesis is true and compute the probability of observing a value of the test statistic as extreme as or more extreme than the observed. By extreme, we mean far from what we would expect to observe if the null hypothesis was true. So again, we can deal with our absolute values of our z alpha, right? Say z alpha over 2 for a two-tailed test. We're looking for the p-value. We're looking for the probability that our mean falls within one of these two rejection regions. Or for the case of the one-tailed test, falls within the either too high for the right-tailed test or too low for the left-tailed test. And what we're interested in is the probability that our p-value falls within that rejection region. That is, it's less. So the p-value test, the way we're going to approach this, is that we're going to state a null and alternative hypothesis test. We're going to decide on a significance level alpha and compute the value of the test statistic from there. We're going to determine the p-value p, and then if p is less than or equal to alpha, we're going to reject that null hypothesis, H0. Otherwise, we do not have enough evidence to reject null hypothesis, and we're going to interpret the result of that hypothesis test when we do it. So this is a 6-step process that we have to make sure that we're following very, very closely if we want to be able to do this. Just a couple quick notes about the p-value. The probability value can be used to judge the strength of the test. And if the p-value is, let's say, greater than 0.1, well, there's really weak or no evidence enough to reject that null hypothesis. And really, depending on the level of the test, our alpha level, right, if we say it's 0.05, then, well, we might have some moderate evidence, but not enough to reject it. On the other hand, if our p-value is less than or equal to 0.5 and greater than 0.01, that might be pretty strong evidence to reject. And if it's less than 0.01, let's say we're using a 95% rejection test, well, we got very strong evidence to reject that null hypothesis. So we're going to go next through some examples that deal with hypothesis tests for the population mean when the standard deviation is known and it's a normal distribution, and one where it's not known. That's coming up next.